This conference will now be recorded.
Sarath, it's all yours.
All right. So, good morning, good afternoon, good evening, wherever you are in the world. And my name is Sarath Jayatilleka. I lead this corporate reliability organization within Daikin Applied. Just to give a little introduction to Daikin, we are a global player. We are number one in HVAC industry in the world, 17 plus billion sales, founded in 1924, present in 1,000 plus locations around the world, 90 production bases, 67,000 plus employees. And the things we make, the chillers, airside solutions, rooftop systems, and air handlers, and water source heat pumps and modular plants, central plants. So I did that to give a kind of idea, and we are in the thermal comfort business, the heating, ventilation, and air conditioning industry. But I put this question to you and this is how it's a kind of a practice question. If you answer one, I know you answered the question one and you said yes. So that's the way our questions, I have 6 questions altogether, how we get the question answers without really stopping our discussion. We could move on and you could punch the number. End of the session, we will do the math and give a feedback to you. Hope that works. So here's the overview. So the first 2, we will go for the product development testing. We'll talk about reliability definitions, how different organizations would view it, and then the methodology. Of course, the viable analysis is a strong method we use, and how we do this testing, accelerated life testing and highly accelerated life testing. So the test data analysis with viable, that's kind of areas we're talking about the challenges and how the solution. So for 6 challenges, then with examples we explain. I probably think that's where this paper caught more attention in the past. I have seen it cited in in books, in PhD theses around the world. So I thought, and Noel and I picked this one, could be the better one to present. So just to give you an idea, we want to pay respect to our gurus. Dr. John Tukey has probably 1/3 of all statistics today. So he's the real classical statistics guru. The accelerated life thing, the classical reliability belongs to, of course, Dr. Weibel and Dr. Nelson, Dr. Maker, Dr. Abernathy. So if you read books, as a starter, these are the books you read, authors you need to read books. Then we have this movement called reliability growth movement. So J.T. Duane publishes 1964 paper. From there, we got this Duane model, 1974. Dr. Crow picked up this idea and he went to another level, and his model is called Crow-EMSA model. So 2 reliability growth, popular growth models are the Duane model and Crow-EMSA model. Then HALT, in late 1970s, highly accelerated life test was introduced. He coined the word HALT. So Dr. Hobbs is the guru for that area. He passed away about 3 years ago, but his books are the classical books to HALT, if you read. So with all paying respect to the gurus, and we'll start rock and roll for a main subject, the product development testing. That's the term I used in the past, and there are other names like new product introduction. That's the term I use today, and new product development, those are the names probably we use your industries. So whichever the name, what we do is we start from the concept on a drawing board. We make a prototype, a show and tell type prototype. Then we develop it to a certain level that makes it a operable component. So we can do some component testing. We put together some operable components and make an operable subsystem. and then we call it operable. We can do some subsystem level testing. Like you had a component called bearing, now you put it into a bearing assembly, and you can test the bearing assembly. Then you do it the operable, put some subsystems into operable system, and you do some system level testing. So you build, you develop, and you build pilots, still system level testing, and you launch the product. So you got system level testing, subsystem level testing, and component level testing. And probably you're familiar with this product development with gate phase model. So you have different gates. You start with concepts, you kind of plan, you design, then you produce, and then you launch the product. During these gate systems, earlier you do the verification testing, and finally you do call validation testing against the user needs. So about 5 to 6 stages during this process. So my next question is, are you using phase gate development process? If you say yes, 2-1, or 2-2 if no. So we talk about these components, subsystems, and systems, but these are very relative terms. For example, if you think of a bearing, the bearing is a little component that goes into your bigger system. But imagine the bearing manufacturer. For him, he has the inner ring, outer ring, balls, cage, lubrication, seal. Those are his components that makes one product called system called bearing. So because of that, these are very relevant terms. This is a conceptual model to say how we do reliability in product design, how we incorporate design for reliability into product development. So this area is called new product development, new product introduction. So we like to make things we try to make it 100% reliable at the, when you introduce. So we probably end up at 99, and then we hand over to manufacturing, and there it kind of drops a little bit under 2% probably. Yeah, that's called infant mortality. Then we hand over to the customer. The consumer will be using, if our system level target is 90% at the end of the design life, probably 10-year, 15-year, 20-year design life is our target for the system. Reliability definitions. So we are going to look at reliability definitions. I know somebody is not muted. I can hear some little noises, but if you would please mute it. Reliability is for a quality person, quality over time. And it's like when you look at quality on day 1, day 2, day 30, 365 days, imagine we have the same quality across the 5th year, the 10th year, the 15th year, across the same quality around the design life. So I sold this idea, performance across the design life, and that's another way to define the reliability. A systems engineer would call it probability of meeting essential requirements across the design life. A marketing person would say a measure of probability that product will not malfunction or fail within specified time limits. So this idea is from Philip Kotler, a marketing guru. But the real reliability, the reliability engineering view would be is the conditional probability. The word conditional is used because a lot of things were given here. The given confidence level, given age, intended function is given. A washing machine, it should be washing only clothes, not tomatoes, not potatoes, which I have experienced in certain countries. The farmers would use it for tomato washing. The real life experience that I had. Of course, specified design life. And then operational environment is given. So we want it to be indoor, not outdoor, that kind of idea. The methodology, viable analysis, and the plots we are going to kind of look at, and then, of course, accelerated life testing, highly accelerate live testing our tools. So a reliability plot, any probability plot would look like this. It's a straight line, and you would probably find like 1% to 99, not 0 to 100. But let's begin with a histogram. We're all familiar with that. When we get this each square, this rectangle put in front of, on top of each other, and we get this cumulative frequency plot. Cumulative distribution function is, when you connect the top midpoints, we get the cumulative distribution function, which is kind of a S shape. If you stretch it, kind of hold it from the two ends and stretch it, you want to make a straight line. And that's what you get in a probability plot, any probability plot. To do that, we really screw up this y-axis, so it's no more a linear axis, and it's true for Weibull analysis. Why do we make it a straight line? Because human eye usually interprets deviation from straight lines, and that's the only reason we do it. There are different names for a probability plot. We call it, statistician would call it cumulative distribution function. Professor Meeker said, it's fraction failure, percentage failures, unreliability. I use percentage failures of the population when I talked about my population out there in field analysis. When it comes to x-axis, it's always the usage time, which could be, for a washing machine, it could be washing cycles. For a bearing inside the washing machine, could be revolutions. Actuations for relays and contactors, on, off, number of hours of operation. And that's how it goes. Now let's look at the Weibull distribution. The Weibull is the parametric distribution. When you say parameter, for example, normal distribution has two parameters, standard deviation and average of the mean. Similarly, we look at Weibull distribution as two parameters. Just to touch, all key functions within Weibull distribution that we used to look are, of course, the probability density function, reliability function, and mostly we look at failure probability or unreliability function. And second most would be the hazard function, called instantaneous failure rate function. Here we are looking at the probability density function. It's right here. And you can see the two parameters like mean and average. Here we have called slope parameter and the characteristic life. You can see those parameters within that equation. Again, the characteristic life has units like hours, cycles, and our challenge is to find what is beta and what is eta. In some industry, like for bearings, we know what is beta. It's normally falling within 1.5. The rest of the functions, three functions from probability, from Weibull distribution, looks like this. And as I said, for a lot of product development testing and even warranty assessments, we use this function a lot. We call it mostly unreliability function. And also this is sometimes we call failure rate, but it's called instantaneous failure rate. And for field data analysis, we would be using this function. So question to you, how many of you use Weibull analysis? The answer is yes, it's 3-1, and otherwise 3-2. Why you use Weibull distribution? Because it's the beauty of Weibull distribution. For example, if the beta value is 3.439, it gives our famous normal distribution. The beta is 1, it gives the exponential distribution. In green, when the beta is 2, you get the Rayleigh's distribution. So this is the beauty of, we can have one distribution that fits into many other distributions. Let's put side by side hazard function and probability density function. Look at the famous bell-shaped curve, which gives the hazard function the failure rate, instantaneous failure function. It's monotonically increasing failure rate, which we don't want to have. look at the blue one, this exponential distribution. This is the constant failure rate. And the Rayleigh's distribution, when beta is 2, is a constantly increasing failure rate. Again, just three famous models. When you read Weibull distribution, the good thing is, more to the right is more reliable, and so you can get the warranty at 365 days, and you come here and go here and find, that's the value for the warranty. And also, if your target is 99.9 reliability, you know exactly at the design life, that's your target. So your product has to pass before launch. Somewhere here, we call it meeting reliability requirements. Anything falling here, we are called under-designed components. These are definitely over-designed components, but a good one probably lying here. So this should happen before launch. Here's the famous bathtub curve. It's a conceptual model of hazard function. And three groups we call infant mortality, where beta is less than 1. And here, the random failures we call, I don't like the word random because nothing is random today. We need to invest and identify what is the cause. But beta is tend to be about 1, and whereas beta goes to about beyond 1. What point here is that, all infant mortalities have beta less than 1, but all beta less than 1 are not infant failures. So that's need to be remembered. Our task is to reduce this line to take close to the y-axis, and then bring this area close to the x-axis. That's our challenge. To give another picture here about the scale, I said they were all we screw up the whole scale to make it a straight line. And look at 9, going from 1 to 10. The 9 is so large here. If you go to the top, 90 to 99 is kind of smaller than this one, and in the middle is much smaller. So it's not definitely a linear line. Here, this is more log line, so kind of equally spaced. And also pay attention, and this is how there's a way to find graphically this beta and eta. How we find eta is we start at 68.2 and go this way. When it hits there, we come down, and we call it that point is called characteristic life. Of course, the slope, you know how to measure the slope. Also, pay attention to this area in the Weibull plot. So F126 means there are a lot of dots here. They probably some dots, more than one dot on each other. So 120, so F equals 126, S equals 8597. So real data from the field of a certain electronic component, and that's how you read the axis and the Weibull plot. Accelerated life testing. The life is an important thing. This should be the design life. If you do not know the design life of your product, you cannot design an accelerated life test. And what's the design life? What is the reliability goal? Are the good questions, for example, to ask yourself, ask any design engineer, and of course, ask your suppliers if you have given them reliability requirements. So somebody say, hey, we do reliability testing. Ask, what's the life? What's the design life? What's the reliability goal? Always a reliability plot. To constitute a reliability plot, the y-axis would be reliability on reliability, where x-axis would be a usage time unit. So if that doesn't satisfy, it's not called a reliability plot. Here, so let's look at highly accelerated life test and accelerated life tests. So the purpose of highly accelerated life test is to recover speedier uncovering of weaknesses and have corrective actions, and also to determine the design robustness. So we need to, at the beginning of a product development, we will be using more HALT, not ALT. But once the product is coming to a higher maturity, we'll be using accelerated life testing, because now we have a product that is mature. We want to know the user level reliability, and also here we may be including, when, because we are highly accelerating certain things, the failure modes we see may not really happen in the real life. And here, at all levels, we'll be seeing all the relevant failures. So that's what it means. When you put it to this plot, log life, log stress life, the proportional area is called old, and more unproportional area is called hold. So if you, for example, you test at 3 levels and can establish the line in pretty short time, we could estimate the normal life. So question 4, how many of you use accelerated life testing? And I said, you should know design life to do that. All right. And because of that, I asked the second question. Do you know your design life? Are you using design life as the key input? Good. So accelerated life tests can be put into 2 different categories, called where accelerated life acceleration factor is about 1, and this is stress testing. And the other case, it is acceleration factor is 1, like time compression. For example, a motor that will be starting at different times, like 5 hours a day. Start stops is the key for a slew bearing in the motor. So, in fact, the start stop is killing factor. So you probably want to count the number of start stops, and that's just time compression. Another example, you'll be running your vehicle like 1 hour a day. If your vehicle is run the same condition 24 hours a day, that is like 1 to 24 time compression. Stress level is different. You like to have about 3 levels of stress testing, and you allocate to different samples. Like one, Dr. Miko recommends 1 to 2 to 4 sample size allocation. Of course, say you put 7 here, you put 14 here, you put 28 here. You put more to this level because you put less to this level because all fail, and fewer will fail here. And those are the kind of glimpse into the accelerated life testing levels. The data will come in 2 categories called complete data and censored data. So when things are, so this is called an event plot. Event plot, in this case, the 5 samples, start time, end time, and these are the failures. So the complete data means every single one failed. So that's a good thing, that situation to get, but in practice, it's not the same. So a lot of in reliability, we had to deal with a lot of censored data. They didn't fail. So censored data, main 4 categories. So let's look how they look like. The event plot, you can see we are here at the present time, and some are still running. So we call unfailed or suspended units, ran out, survivors. And in fact, reliability is due to the survivals, not failures. So here 4 failures, and others are running. Time censored. So that's what it means is we say, hey, we are going to run this test, but we are going to stop at certain time. We are lucky if we get some failures. But I prefer the other one we call failure censored data, because a lot of time I give my suppliers that, hey, you run the sample size, but when you see 8 samples or 5 samples, you can stop. Yeah. So in this case, it's 5 number of failures that when the 5th failure happens, you stop the test. Interval data. So these are happening in intervals. For example, I tell my lab tech to watch it. By 6 p.m. he leaves the office, and 6 a.m. next day he would come back and look, and he finds some had failed. We don't know exactly when they fail. So we are called interval data. All right. So that's we looked at how the tools and how the data looks like, and this is where we are going to look into the those techniques, the challenges. So A to F, I think 6 challenges and kind of solutions. So the number of components is huge. Any component in a washing machine, probably 400, in some systems, thousands. In really applications, about 80% to 90% are like 100% reliable. They don't fail during their design life. But of course, the other 10 to 15% give the trouble. So we don't really do we really have to test all single component level testing? The answer is yes, when they are underdeveloped. For example, if you are producing a component that is brand new, never occurred in the world, it's the first time of developing it. So you need component level testing. But if you buy something from the shelf, off the shelf item, being tested, time tested over and over years by other suppliers in the industry, you don't really have to do it because again, number of uh, is huge number of components. But if you, the problem is, if you then one thing is it's difficult to simulate the operating condition when you use, say, a bearing. The bearing interacts with other components, with the shaft, the bearing assembly, axial loads, fluctuating axial loads and radial loads. So therefore, it's little value determining the absolute reliability. So the strategy here is we go to subsystem testing. Now, say a washing machine has uh, 400 parts, but you have about 5 subsystems: control system, suspension, the motorized system, the enclosure, suspension. So few subsystems. But the advantage is when you do the subsystem level testing, not only you get the subsystem level reliability, you even get the component level reliability. And the results are more relevant and accurate because they interact with the right parts. And also, it reduces the large number of component level testing. That's a good idea to begin with. The second idea is the failure mode wise reliability analysis. So each failure mode has its own unique distribution, uh, and they have their own. I mean, if you push, at the very, if you find different failure modes, a mix of failure modes, you put into one distribution, you will see very unfit curve. So the right thing to do is to do, isolate by failure mode and do the failure mode wise analysis. And how it is done is you right censor the other failure modes and when you want to look at one failure mode. So the benefits are you focus on one failure mode individually and thereby you know the impact of the reliability growth if you fix that. And that's the main advantage. I mean, when you want to talk to your management, hey, we fix this problem first because the impact of that is the return on investment on that failure mode can be visible. So that's the best advantage of the failure mode wise analysis to justify the resource allocation based on the impact. Now here is an example. The shaft, we could call a shaft failure. But shaft had 2 different failures, fatigue failure and the general wear. And when I put all this data, I have this data here, I put all in one and I can get just one line. But the right way to do is to do 2 lines. Right censor the shaft wear and look at the fatigue, and then do the other thing. Use right censor the fatigue and look at the shaft wear. And the multiplication of any data point, any timeline point, the reliability would be the product of the 2 reliabilities would be the exact reliability, the right reliability, not put all the failure modes into one. So we encourage the failure mode wise reliability. This is called nearest slope for improved zero failure design. So this situation comes, during your new product development process, when reliability improves, parts don't fail. They improve now. They don't fail. So we don't have dots on the plot. So improvements cause failures to delay. I mean, everything one day fails, but not within your design life. The failure distributions shape, like beta parameter, will remain unchanged. So similar distributions carry same beta shape parameter. Only thing is, eta, the characteristic life, changes. So therefore, use the nearest slope for the beta with zero failure design. So here's the example. So this is something I did in the very past. So this is published data, so I could even get the data and where I did it. Um, so very first line is the first design iteration early. You can see different failure modes here. It's one failure mode, 2, 3. And you fix those, and now you test the second design iteration. It's moved here, and it has two different failure modes. You can see one is here, one is here. And so once you fix that, it moved to the right a lot, and then that is, you get some more failures. So you got 34 failures, and you improve that and go to the next level, and you get one, keep reducing, and finally, it's my design target. So my target is 99% reliability or 99.9 reliability. I do it to the last, but the last one I don't have dots. But what I do can see is these lines get steeper and they get parallel. So in the last one, you have zero failures, but you can borrow the beta parameter from the other one and analyze and even draw the line. That's the idea, that borrowing the nearest zero failure design, borrow the slope from the nearest slope. So this is the other, the good situation, that you use test fixtures. Say you want going to test a subsystem, and now you have made subsystem testing. You have a fixture to test your bearing assembly, say, and all the suspension units or the springs. And your test fixture also has problems. So not only you improve your test fixture from your first design iteration to the next level, you fix your product problem, the subsystem problem, but you debug your fixture also. And by the time you get the well matured product, you make your fixture very correlated to the real life application, and the results have more value now. Good. And in this case, is a bearing assembly. It passed your target point, and so that's where you stop your test. Here's what we use ALT here. Excuse me, the comparison of some design options, or could be options of supply options, design options, material options, and we could use accelerated life tests or highly accelerated life tests to verify, find the right spring, right material, right design option. So, for example, let's look at the example. Here's a hydraulic system, and within those valves, directional controls valves, we have these little springs going on. So I have a lot of suppliers coming into that.
Even though we are requesting to implement the site safety appointed computer safety officer.
So I have this suppliers after I test. So I test them all in one unit. I could do this testing in 2 weeks. I probably make everything to fail. I put those different suppliers values into viable plot, and here's my target, and I know the winner right away. So I would be working with this supplier, not the other supplier. So that now this valid not only for suppliers, different design options, different materials. We could qualify through very decisively. We can decide on those options, and these are things that we come across every time. Here is an example. So I have a belt. It's a belt, that goes across the washing, the dryer system, the clothes dryer. This belt goes across the dryer. There's a motor, and we have an idler pulley right here, which creates certain reverse bending, and it prays the belt, and that's the failure mode. So I make this test fixture called serpentine test fixture, and I create reverse bending because that's my main failure mode. So I create reverse bending. This is a drive pulley. I can give different loads here, and I drive it here at the speed I want, and I can make all of them fail. And this is my existing supplier. So I took them existing suppliers belts and put in this fixture, and I have these values. If it means all failed. And then the new supplier came, and they said they're more repeated, they survive better. And I put them, I got only a few samples. I put them into the same test fixture and got my results. Then I put them into viable plant. And right away, I have a winner. So I know I should be changing to supply the quality, not a cost improvement, but it's also a quality improvement, design life improvement. And this is the last the strategy that I'm trying to look, but I'm going to take a little more time for this one. So we're trying to correlate the life cycles to accelerate life testing. So let's look in the normal operating cycles, the damaging cycles and non-damaging cycles both occur. Certain cycles damage a lot. And when it comes to accelerated life tests, we don't want to count on non-damaging cycles, waiting time. We only concentrate on the damaging cycle, and that's how we do the time compression. But when you do this, this is in the normal life operation, probably operation in hours. But when it comes to here, it's just one cycle, or one damaging cycle, start, stop, or on, off, something like that. This creates a mismatch between the time. So how do we compress the time and go back to the predict the design life in real life? So what the strategy is, many products do not continuously use. If you listen to your home refrigerator, it has to work 24/7, but if you listen to the motor, it's not going to work probably 1 minute during first, every half an hour it works 1 minute. So that's a lot of waiting time. Look at the door of your refrigerator, how many times it would open. So we can capitalize on this. So this is the time in real life, and it's the compressed time. So your acceleration factor is the big T divided by the small t. Here's a similar thing. So in real life, you got damaging cycles and non-damaging cycles. And the test fixture, you would be only counting on those cycles. So here is a field scenario. So let's say number one is you find some some certain things are failing in the field. But your target is here. You want something right here, but they're failing before the target reliability. Now you make a fixture. You get the same batch and simulate the same testing, and then you reproduce the same failure mode right here. So you now have field data and you have a test fixture that reproduce the same failure mode. So now you have a transfer factor from field data to the fixture test. And using that transfer factor, you can transfer that real target to the fixture target. And you do your reliability testing of the improvements. You do your improvements until you get your improved design iteration that passes the fixture target. And now you can apply it to your real life machine because you know that's going to meet your real life reliability target. So that's a pretty good idea when you do the fixture testing. So in so I have a real life example. I experienced a very late life fatigue failure, like in a 20-year design life product, a 15th year failure. And what we do is we made a test fixture. So this one is in washing machines, the washing cycles is the real life design life the cycles. The test fixture is number of revolutions. So this is the field failure we got. And here's the fixture test we made. So I have a transfer factor, different time units, washing cycles, and this is a number of revolutions. And we improved our product until we passed this, because we knew we transferred our real life reliability into number of revolutions, the washing cycles to revolutions. And then we launched this product because we passed our reliability target in terms of the number of revolutions in the fixture, which is actually passing our washing cycle target. And that in the equation, when you translate really that revolution to revolution kind of nullify, and your answer comes in washing cycles. So that's kind of the idea. You don't have to worry about this mix of the transfer factor is a mix of units, but in the end they nullify. So that brings to my sixth question. Did this presentation going to impact your current thinking of reliability practices? So reliability is the term used in very social meaning, very social applications. Like it's a 200-year-old word, but it had been used in social setting. In your organization, it may be using in a social setting. Somebody say, "I'm doing reliability testing," they didn't really mean it. But there's a scientific meaning. Good. In summary, we did reliability definition. We did viable analysis and HALT accelerated life testing. We talked about viable solutions. So in summary again, use subsystem level testing for component and subsystem level testing because it demonstrates not only component but subsystems too. Also do viable mode, failure mode wise analysis. Don't throw all your failure modes into one. And then early testing with simulated fixtures is going to help a lot as the product get matured, because your fixture get matured and you're going to reflect the real life failures in your fixture. The idea about nearer slope, as the reliability grows, things don't fail, but you can borrow your previous slope to do your analysis even if you have zero failures. HALT, you can use HALT in the early product development and also later the accelerated life testing. But to compare design supplies and material options, you can use HALT testing. Great, thank you very much, and I'm open to questions.
Thank you, Sarath. The first question I see is, will a copy of the presentation be available?
So I think you are going to put it in the YouTube, right? I mean, your
Correct.
section. Yeah. So probably I could provide a copy.
Okay, that'd be great.
Yeah.
Any other questions? Well, while we're waiting here, our next webinar will be on Wednesday, October 10th. It's employee empowerment using military tools to support your organizational culture with Cynthia Young of McKean Defense. So we still have space available if anybody would like to register for that one next Wednesday, if you haven't already done so. Sarath, I'm not seeing any other questions at the moment.
Okay.
Oh, wait a minute. No, wait a minute. We just had one come up here. Can we use the same kind of analysis when using an expensive system with very little failure record?
Yes. Now, I'm not sure when you mention very little failure records in the field, and I think that's how the understanding. And very little failures in the field for how long is a factor. Do you have a design life, say 10 years? For 10 years, very little failures. Yes, and that's the way we use the field data analysis all the time. And most of these, I can show some examples that using failure data in different papers actually. Okay, give me a second. That one. So this is actually a field data, and you can see massive sample size in the field, and only 126 failures. And we use that data to predict the design life, analyze the field data. So the Bible is a tool not only for product development, but it's also for the product, field data analysis. So answer is yes. And most probably your data, the y-axis, x-axis would be the number of days in service, which is a fielded product. Hope that answers the question.
Okay. Any other questions from folks here? We still have a few minutes. Okay.
The quality, when I kind of mentioned the quality, you think of the first year, 30 days, 365 days, but how do we give the quality for the 5th year, for the 10th year, for the 15th year, for the 20th year? That's the idea, how we ensure that quality across the design life. And that's, we pay little attention to that area. And that's how the reliability movement came in. The birth of probably reliability is the World War II, and that got momentum. Even Dr. Weibel worked for NATO, and his publication came in like 1939. And we are into this world today. The RAMS has been there for 65 years. But if you are a company that embraces reliability, Weibel analysis is something you really embrace.
Okay, well, we still have a few more minutes for questions. If anybody has anything, we do have the time to answer it. Sarath, any other closing comments?
Thank you very much for arranging this, Noah, and also, I think it's a good opportunity that I got this, to present. My vision for my company is to make my brand name the most reliable HVAC in the marketplace. But reliability is a good thing; it's the best thing for the earth, for the green environment, for the customer, because your things don't fail during that intended design life. So is something we all should embrace and kind of study and improve our product reliability. It should be a part of quality, and it is a part of quality, but paid little attention. So thank you very much.
Thank you. And let's see, we have another question from somebody saying that they were taken away during the presentation. Will a copy be available after the meeting? And I think you mentioned that
Yes.
we're going to make a copy available, so that's the answer.
Yes.
I think we're going to go ahead and call it for today. Thanks again, Sarath, for presenting for us today. We'd also like to thank everyone for joining us. Our next opportunity will be Wednesday, October 10th, 12 noon Eastern time. Until that time, we'd like to wish everybody a great rest of the day, and we'll see you soon. Thanks. Bye.